Buckle up, it's space-time. Number 10. Vacuum decay. In 1980, physicists Sidney Coleman and Frank Luccia published a paper in Physical Review D that many of their colleagues found so deeply unsettling they quietly set it aside and moved on. The two researchers had done the mathematics on what happens if the universe's lowest energy state is not actually the lowest energy state possible. The answer they arrived at was something for which no warning system could ever exist, no telescope could ever detect, and no civilization could ever survive. The universe, as far as we can tell, exists in what physicists call a vacuum state. Quantum field theory tells us that empty space is not truly empty. It is a seething ocean of energy fields, and the level at which those fields currently sit determines the rules of physics. The strength of gravity, the behavior of electromagnetism, the mass of every particle in existence, all of these depend on the current energy configuration of the vacuum. In 2012, the Large Hadron Collider at CERN confirmed the mass of the Higgs boson at approximately 125 gigaelectronvolts. According to standard model calculations, that measurement places our vacuum uncomfortably close to the boundary between stable and metastable, which is to say, not permanently settled but merely resting. A metastable vacuum can decay. Somewhere in the universe, through a process called quantum tunneling, a region of space could spontaneously collapse to a lower energy configuration. This would not be an explosion. It would be something far worse. A bubble of new vacuum would form, its wall expanding outward in every direction at the speed of light, rewriting the fundamental constants of physics as it traveled. Inside that bubble, the strong nuclear force would no longer function as it does. Atoms could not form. Chemistry would be impossible. The concept of matter itself would become meaningless. The truly harrowing detail is the geometry of how this would reach us. The bubble wall travels at 186,000 miles per second. No signal, no light, no radiation of any kind would precede it. There would be no precursor. The first sign of vacuum decay arriving at Earth would be simultaneous with the last moment of existence. Every particle in your body would be restructured into something incompatible with life, matter, and physics as we know them, all before a single neuron could fire in response. What makes vacuum decay different from every other item on this list is that it requires no external catastrophe, no collision, no dying star. The universe itself may carry the seed of its own dissolution quietly encoded in the mathematics of the Higgs field. The question is not whether the vacuum could decay. According to the physics, it can. The only question is whether it already has, somewhere, and how much of the speed of light remains before that information reaches us. Number 9. The Big Rip. On February 25, 2003, physicist Robert Caldwell of Dartmouth College submitted a paper alongside colleagues Mark Kamiankowski and Nevin Weinberg of Caltech that proposed one of the most viscerally disturbing endings the universe could suffer. Published in Physical Review Letters that August, their work explored what happens if dark energy is not merely accelerating the expansion of the cosmos, but growing stronger over time. The name they gave to this endpoint was the Big Rip, and once you understand the sequence of events they calculated, the name feels entirely appropriate. To understand the Big Rip, you need to understand dark energy. Discovered in 1998 by astronomers Saul Perlmutter, Brian Schmidt, and Adam Rees, dark energy is the mysterious force driving the universe to expand at an accelerating rate. It currently comprises approximately 68% of all the energy in the cosmos. In the standard model, dark energy is constant, a steady background pressure built into the fabric of space. But Caldwell and his colleagues explored a different possibility. What if dark energy has an equation of state where this ratio of pressure to density falls below -1? They called this hypothetical form phantom energy, and its defining characteristic is that it intensifies as the universe expands. If phantom energy exists, it will eventually overcome every force in the universe in a specific, calculated sequence. Galaxy clusters will be torn apart roughly 200 million years before the final moment. The Milky Way itself will be ripped apart about 60 million years before the end. Our solar system will cease to hold together a few months before the end. Earth will be pulled from the sun's gravity and destroyed approximately 30 minutes before the last moment. Then, in the final seconds, molecules will be torn apart, atoms will be shredded, and even atomic nuclei will be destroyed roughly 10 to the power of 19 seconds before the absolute terminus. The unsettling reality is that we cannot currently rule this out. Measurements of dark energy's equation of state are not yet precise enough to confirm whether its value is exactly -1 or slightly below it. The difference between those two scenarios is the difference between a cold, quiet heat death and a violent, systematic dismantling of everything that exists. Current experiments, including observations from the Euclid Space Telescope launched in 2023, are attempting to constrain this value with greater precision, but the answer is not yet in. The Big Rip is unique among cosmic doomsday scenarios because it is both plausibly supported by existing physics and almost completely undetectable from inside the process itself. Each stage of destruction would simply happen. There would be no warning because the force causing it is invisible, pervasive, and measured only by its effects. The universe would end not with a catastrophe arriving from outside, but with the very fabric of space turning against everything it contains. Number 8. A rogue black hole. In August 2011, two ground-based telescope surveys called the Microlensing Observations in Astrophysics Program and the Optical Gravitational Lensing Experiment detected a peculiar brightening of a star in the direction of the galactic center. Something invisible had passed in front of it. Over the following 6 years, astronomer Kailash Sahu of the Space Telescope Science Institute in Baltimore used the Hubble Space Telescope to track the warping of that background star's light with extraordinary precision. The results, published in the Astrophysical Journal in 2022, announced the first confirmed detection of a lone, isolated stellar mass black hole wandering freely through our galaxy, with no companion, no accretion disk, and no light of any kind. The object, catalogued as MOA-201-BLG-191/OGLE-2011-BLG-0462, has a mass approximately 7 times that of our Sun. It is located roughly 5,000 light-years away in the Carina-Sagittarius spiral arm of the Milky Way. It is moving at a transverse velocity of about 45 kilometers per second relative to surrounding disk stars, a speed consistent with having received a natal kick during the supernova explosion that created it, sent careening through interstellar space like a cannonball fired in the dark. The discovery was only possible because of gravitational microlensing, the bending of background starlight by the black hole's gravity. There is no other technique available to find these objects. They emit nothing. That last point is important. This black hole was detectable only because it happened to drift in front of a star precisely aligned with Earth. How many others have passed in front of nothing, seen by no one? Astronomers estimate that approximately 100 million stellar mass black holes roam our Milky Way. Most have never been catalogued. Most never will be. Sahu's team calculated that based on this discovery, the nearest isolated stellar mass black hole to Earth may be as close as 80 light-years away. That is close enough that if it were on a direct trajectory toward our solar system, the first sign of its approach would be subtle, gradual perturbations in the orbits of the outer planets, potentially decades before any catastrophic disruption. A rogue black hole entering the inner solar system would not collide with Earth like an asteroid. It would instead gravitationally rewrite the solar system's architecture. Planetary orbits could be destabilized. Earth could be flung outward toward the frozen outer system or inward toward the Sun. The black hole itself would never be seen coming. By the time its gravitational influence became measurable to our instruments, the outcome would already be determined by celestial mechanics, operating on timescales too large for any human response to alter. Of the estimated 100 million black holes drifting silently through our galaxy, none have been tracked, none have known trajectories, and none have sent us any signal of their presence. We found one only because it briefly passed in front of a distant star. The others, by definition, are the ones we have not found yet. Number 7. Heat death. The concept has been mathematically established since 1865, when physicist Rudolf Clausius formulated the second law of thermodynamics. It does not require exotic particles, undiscovered forces, or speculative cosmology. It requires only one thing: time. And the universe has a supply of time so vast that every number used to describe it requires its own level of scientific notation to write down. The scenario is called heat death, and unlike every other ending on this list, the overwhelming consensus of physics is that it is not a possibility. It is an inevitability. The second law of thermodynamics states that the total entropy of a closed system always increases over time. Entropy is essentially a measure of disorder, of energy becoming less available to do useful work. The universe is a closed system. Its entropy increases with every star that burns, every explosion that dissipates energy into space, every photon that crosses the void and is absorbed into cold matter. This process is irreversible. The universe moves in one direction, toward maximum entropy, and it has been moving that way since the first fraction of a second after the Big Bang. The destination at the end of this journey is a state of absolute thermodynamic equilibrium. No temperature gradients, no energy differentials, no processes of any kind. The timeline is staggering in a way that makes it almost impossible to hold in the mind. All stars in the observable universe will have burned out within approximately 100 trillion years, which is 100,000 billion years, which is roughly 7,000 times the current age of the universe. Black holes, the last major energy structures in the cosmos, will evaporate through Hawking radiation on timescales between 10 to the power of 67 and 10 to the power of 100 years. After that, the universe will contain only cold, diffuse particles spread uniformly across an ever-expanding void, with no clumping, no interaction, no change of any kind. What distinguishes heat death from other cosmic doomsdays is its absolute certainty, and its absolute silence. There is no moment of destruction. There is no catastrophic event. The universe does not end so much as it runs out of things to do. The cooling is gradual over timescales that dwarf everything else on this list combined, and there will be no observers remaining to witness the final state because the conditions that permit the existence of observers will have been absent for incomprehensible stretches of time. Heat death is the only ending that requires no catastrophe and no external force. The universe contains within its own fundamental laws the instructions for its own eventual quieting. Every star that rises in the night sky is burning through the finite reserve of energy that makes complexity and life and thought and observation possible. The lights are on. They have been on for 13.8 billion years. The second law requires that they go out. Number 6. A nearby gamma-ray burst. On December 27, 2004, at 21:30 Universal Time, a wave of gamma rays and X-rays from deep space struck Earth's upper atmosphere. More than a dozen spacecraft detected it simultaneously, including NASA's Swift Observatory, the European Space Agency's Integral Satellite, the Cassini probe near Saturn, and the Mars Odyssey orbiter. Swift's detectors saturated completely, even though the satellite was not pointing anywhere near the source. The radiation was so intense that some of it reflected off the surface of the moon and was detected a second time. It had traveled 50,000 light-years to reach us. It had come from a magnetar on the far side of the Milky Way called SGR 1806-20. It partially ionized Earth's upper atmosphere and caused our planet's magnetic field to ring like a bell. The magnetar SGR 1806-20 is a neutron star roughly 20 kilometers across, wrapped in a magnetic field over a quadrillion times stronger than Earth's. In 1/10 of a second, it released more energy than our sun produces in 150,000 years. The burst was the brightest event ever detected from outside the solar system, and it is important to note that it was not a gamma-ray burst in the classical sense. It was a magnetar flare, a comparatively localized event. A true long gamma-ray burst, produced by the core collapse of a massive star, can sustain that kind of energy output for seconds to minutes across a focused beam, releasing more energy in that time than the sun will produce across its entire 10 billion year lifespan. Astronomers broadly agree that a long gamma-ray burst aimed directly at Earth from within roughly 6,000 to 8,000 light-years would be catastrophic. The beam of high-energy radiation would strip away the ozone layer globally within seconds. Ultraviolet radiation from the sun would then reach Earth's surface unfiltered. Photosynthesis would collapse. The food chain would collapse with it. Some researchers, including a 2004 study published in the International Journal of Astrobiology by Adrian Mellett and colleagues at the University of Kansas, have proposed that the late Ordovician mass extinction, approximately 443 million years ago, which eliminated around 85% of marine species, may have been triggered by exactly this mechanism. The defining characteristic of a gamma ray, burst as a threat, is its undetectability. The radiation travels at the speed of light. There is no advanced messenger, no gravitational wave precursor on a meaningful timescale, no neutrino burst that our current instruments could process and translate into a warning before the beam arrived. The first sign of a gamma ray burst aimed at Earth from within the danger zone would be the last thing our atmosphere experienced before the damage began. Somewhere in the Milky Way right now, massive stars are in their final stages of existence. Most will collapse in directions that pose no risk to us, but the geometry of the galaxy is indifferent to our preferences, and we have no catalog of which stars are aimed our way. Number 5. The dark matter catastrophe. In the 1970s, astronomers Vera Rubin and Kent Ford of the Carnegie Institution of Washington made a discovery that quietly rewrote the inventory of the cosmos. Studying the rotation curves of spiral galaxies, including our own Milky Way, they found that the outer stars were orbiting too fast. According to Newtonian mechanics and the visible mass of those galaxies, those stars should have been flung outward long ago. They were not. Something was holding them in place. Something massive, distributed throughout and around each galaxy in a vast halo, providing gravitational scaffolding for everything we could see. That something had no light, no electromagnetic signature, and no interaction with any instrument we possessed. Astronomers called it dark matter, and it comprises approximately 27% of all the energy in the universe. To be precise about what that means, 27% of everything is made of a substance that does not emit light, does not reflect light, does not absorb light, and does not interact with electromagnetic radiation in any way detectable by our current technology. Ordinary matter, everything you have ever seen or touched, every star, planet, gas cloud, and galaxy visible to every telescope ever built, makes up approximately 5% of the cosmos. Dark matter is more than 5 times as abundant as everything we have ever observed. We know it exists because of what it does to the things we can see. We have no confirmed direct detection of what it actually is. The leading candidates, particles called WIMPs and axions, have been searched for extensively by experiments including the LX-Zeppelin detector in the Sanford Underground Research Facility and the Xenon 1T experiment in Italy. Neither has produced a confirmed signal. The Milky Way is embedded inside a dark matter halo estimated to extend several 100,000 to perhaps 1 million light-years in every direction, vastly larger than the visible disk of the galaxy. Billions of dark matter particles are passing through your body right now, through the walls of every building, through the Earth itself, without interacting with any of it in any detectable way. Under currently understood physics, this is benign. The terrifying implication is the qualifier in that sentence, currently understood. We have built our entire physics infrastructure to detect things that interact with electromagnetic radiation. Every telescope, every detector, every particle accelerator operates on the assumption that the things worth measuring leave a signal in light or in forces we understand. Dark matter, by definition, does not participate in that framework. If dark matter has properties, interactions, or phase transitions that we have not yet modeled, our instruments would register nothing until the effects became visible through their impact on ordinary matter. The warning system for a dark matter catastrophe is the same as the warning system for vacuum decay. There is not one. We are not outside of the dark matter. We are inside it, surrounded by it, threaded through with it. 27% of the universe is a substance we cannot see, cannot touch, cannot measure directly, and cannot predict the full behavior of. Whatever dark matter can do, we will learn about it only after it has already done it. Number 4. The false vacuum collapse. In 1928, physicist George Gamow used the mathematics of quantum tunneling to explain a phenomenon called alpha decay, the process by which unstable atomic nuclei shed particles through a quantum mechanical shortcut that classical physics said should be impossible. The principle he was working with had already been experimentally confirmed and is, in fact, the foundational mechanism behind the operation of every transistor in every electronic device on Earth. Quantum tunneling is not theoretical. It is how the world works. Now consider what happens when you scale that principle up from the nucleus of an atom to the entire structure of the universe. In 2012, scientists at CERN measured the mass of the Higgs boson at approximately 125.25 giga-electron volts. This measurement was celebrated as one of the great triumphs of modern particle physics. It was also, for cosmologists who understood its implications, faintly alarming. A paper published in the Journal of High Energy Physics by Espinosa and colleagues, and subsequent analyses by researchers including the groups responsible for the Standard Model's most precise calculations, confirmed what the measurement implied. Our vacuum sits close to the boundary between absolute stability and metastability. The Higgs field, the quantum field that permeates all of space and gives particles their mass, may not be in its lowest possible energy state. It may be resting in a local minimum, like a ball sitting in a shallow bowl on a hillside, stable enough to remain for billions of years, but not permanently settled. If the Higgs field is metastable, it can tunnel through its energy barrier to a lower state. This is the false vacuum scenario. Unlike vacuum decay triggered by a single region's spontaneous transition, a tunneling event nucleating anywhere in the observable universe would propagate as a bubble expanding at the speed of light in all directions. Inside the bubble, the Higgs field settles to a new, lower energy state. In that new state, every fundamental constant of physics changes. The masses of quarks and electrons would be different. The balance of forces that permits atoms to form, that allows chemistry to function, that permits matter as we understand it to exist at all, would be rewritten according to a new set of rules incompatible with our current reality. The distinction between this scenario and vacuum decay is one of mechanism rather than outcome. Both are plausibly grounded in the confirmed properties of the Higgs field. Both result in the complete replacement of our physics with something else. Both are undetectable until the moment of arrival. What makes the false vacuum particularly resonant is the way it reframes existence itself. We may not be living in the universe's final configuration, but merely in a temporary arrangement, a local minimum of energy masquerading as the permanent ground floor of reality. The vacuum you are sitting inside right now might not be the bottom. Somewhere in the space between the atoms of your hand, in the quantum field that fills every cubic millimeter of empty space on Earth and across the cosmos, the mathematics of the Higgs potential describes a gentler valley just below where we currently rest. And quantum mechanics does not require permission before it finds it. Number 3, the Andromeda encounter. For most of the 20th century, astronomers knew that the Andromeda galaxy was approaching the Milky Way, but could not determine whether a collision was inevitable. The galaxy's radial velocity, its speed directly toward us at approximately 110 kilometers per second, was measurable. Its transverse velocity, its sideways motion relative to our line of sight, was far harder to pin down, and without knowing that number, the trajectory remained uncertain. In 2012, astronomer Roland von der Marle of the Space Telescope Science Institute and his colleague Sangmo Tony Zone published a paper in the Astrophysical Journal that seemed to settle the question. Using 7 years of Hubble Space Telescope observations to track the positions of individual stars in Andromeda against background galaxies used as fixed reference points, they concluded that the two galaxies were on a near head-on collision course. The headline was immediate. In approximately 4 billion years, the Milky Way would cease to exist in its current form. Andromeda, also cataloged as M31, currently sits 2.537 million light-years away. It is a spiral galaxy broadly similar to our own, containing roughly 1 trillion stars, compared to the Milky Way's estimated 300 billion. On a clear, dark night far from city lights, it is visible to the naked eye as a faint elongated smudge in the constellation Andromeda, the most distant object a human being can see without any optical aid. What you are looking at when you find it is a galaxy of 1 trillion suns currently traveling toward you at 110 kilometers per second. Every second that passes while you observe it, it is 110 kilometers closer. Then, in 2025, a team led by Til Sawala using combined data from the Hubble Space Telescope and the European Space Agency's Gaia spacecraft reanalyzed the trajectory with updated measurements and arrived at a far less certain conclusion. Taking into account the gravitational influence of the Large Magellanic Cloud on the Milky Way's path, they found approximately a 50% probability of collision within the next 10 billion years, and a roughly equal probability that the two galaxies would miss each other entirely or pass at sufficient distance to avoid a merger. The fate of our galaxy, it turns out, is a coin flip. If the collision does occur, individual stars will almost certainly not collide. The distances between them are simply too vast. But gravitational tides will reshape both galaxies profoundly. Star formation will ignite. The solar system may be flung outward to a new position in the merged structure, which researchers have taken to calling Milkomeda. The night sky, over millions of years, will transform into something unrecognizable, a new configuration of stars and gas, and the gravitational fingerprints of two spirals becoming one elliptical. Right now, in the constellation Andromeda, you can see it with the naked eye. 100 billion stars moving toward us at 110 kilometers per second. It has been coming for billions of years. Whether it reaches us depends on measurements so precise that even our best current instruments leave the question unresolved. The galaxy that may consume ours is already the most distant thing you can see without a telescope, and it has been there every clear night of every human life ever lived. Number 2. The Big Crunch and the Cyclic Abyss. For most of the 20th century, cosmologists considered the Big Crunch a serious candidate for the universe's ultimate fate. Alexander Friedman's 1922 solutions to Einstein's field equations showed that if the density of the universe exceeded a critical threshold, gravity would eventually overwhelm the expansion, reverse it, and collapse all of space and time back into a singularity of infinite density. The universe would end the way it began, in a point of everything compressed into nothing, a mirror image of the Big Bang playing in reverse. Then, in 1998, astronomers Saul Perlmutter, Brian Schmidt, and Adam Riss discovered that the universe's expansion was accelerating rather than decelerating, driven by the dark energy that would eventually earn all three researchers the Nobel Prize in Physics in 2011. The Big Crunch seemed to be ruled out. The universe, it appeared, would expand forever. The unsettling development came later. Physicists Paul Steinhardt of Princeton University and Neil Turok, then at Cambridge, developed what they called the cyclic cosmology model, published in a landmark 2002 paper in Science. Their model proposed that the Big Bang was not a beginning, but a transition, one phase in an endless sequence of expansions and contractions, each cycle replacing the previous one entirely. In their framework, dark energy does not remain constant forever. It eventually weakens, allowing gravity to reassert itself. The universe contracts. It reaches something approaching a singularity. And then, through mechanisms rooted in string theory and the dynamics of extra dimensions, it bounces, producing a new Big Bang with slightly different initial conditions. The previous cycle is not remembered. Its structures, its stars, its civilizations, its entire physical history are erased and replaced. The most philosophically disturbing element of cyclic cosmology is not the ending, but the erasure. Every physical record of a cycle is destroyed in the transition. If our universe is one iteration in an infinite series of such cycles, there is by construction no information preserved from previous cycles that we could ever detect. We would have no way of knowing how many times this has happened. We would have no way of knowing whether the physical constants of our current universe were chosen to be what they are, or simply emerged from the chaotic transition of the last bounce. The question of whether anything is unique about our existence becomes, in a cyclic universe, meaningless. Everything has happened before, in configurations we cannot access and cannot remember. Current observations cannot definitively confirm or rule out the cyclic model. The central question is whether dark energy's equation of state, currently measured near -1, could evolve over vast timescales in a direction that allows gravitational reconquest of the expansion. The precision required to answer that question definitively exceeds our current instruments. Ongoing surveys, including those from the Euclid mission and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, may eventually constrain the answer. What the Big Crunch and the cyclic model share is an implication that redefines the scale of what might be lost when the universe ends. Not just our civilization, not just life, not just complexity, but every atom of every structure that has ever existed, collapsed and reborn as something with no memory of what came before. Compared to that, every other entry on this list is merely a local catastrophe. Number 1. The end of time itself. Every scenario described in this video has shared a quiet assumption that after the universe ends, time continues, that there is a before and an after, that the ending is an event, a moment with the location in the sequence of moments, a point on the timeline even if nothing survives to observe it. That assumption is so deeply embedded in how we think that we rarely examine it. In 1986, physicist Carlo Rovelli, then at the University of Padova, began developing a framework for quantum gravity that would eventually lead him to a conclusion his colleagues found both rigorous and profoundly disorienting. Time, as a fundamental feature of the universe, may not exist at all. The theory Ravelli developed alongside Lee Smolin and others over the following decades, known as loop quantum gravity, describes space and time not as a fixed background stage on which physics happens, but as emergent properties arising from the relationships between quantum states. In this framework, time does not flow independently of matter and energy. It is produced by them. It is a relational quantity, meaningful only when something is changing relative to something else. This is not philosophy. It is a mathematically rigorous attempt to reconcile general relativity with quantum mechanics, the two most precisely tested theories in the history of science, which are notoriously fundamentally incompatible with each other. The resolution of that incompatibility may require abandoning the concept of time as a fundamental dimension. If time is emergent, then in a universe approaching maximum entropy, as all structure disappears, as all energy gradients flatten, as all processes cease, the conditions that produce the experience of time cease with them. This is not the same as time stopping. It is the more radical claim that time, in the absence of the physical processes that generate it, has no content and no meaning. The physicist Julian Barber, in his 1999 book, The End of Time, argued for a block universe in which all moments exist simultaneously, and the sensation of time passing is a feature of our particular configuration of matter, not a feature of the universe itself. In this view, the universe does not end in time. It simply exists as a complete static structure, and our experience of moving through it is an artifact of the arrangement we happen to occupy. The Boltzmann brain thought experiment, formalized by cosmologists including Raphael Bousso of the University of California, Berkeley, adds a further layer of vertigo. In a sufficiently old universe approaching heat death, quantum fluctuations will, over timescales of 10 to the power of 10 to the power of 50 years, spontaneously produce self-aware observers with false memories of having lived in a structured universe, far more often than structured universes produce observers through the slow accumulation of complexity. If time continues long enough, you are statistically far more likely to be a Boltzmann brain, a momentary fluctuation in empty space with illusory memories, than a product of 13.8 billion years of cosmic evolution. The mathematics does not care which interpretation you prefer. These ideas converge on a conclusion that sits beyond the reach of every other item on this list. Vacuum decay destroys matter. The Big Rip destroys structure. Heat death destroys usable energy. The end of time does not destroy anything. It dissolves the frame within which destruction is possible. It is not the last event. It is the condition in which the concept of events no longer applies. Every other ending on this list can be imagined from outside, described as a moment placed on a timeline. This one cannot. It is not the universe going dark. It is not the universe going cold. It is not the universe going silent. It is the universe reaching the condition in which the words dark and cold and silent, which all describe the absence of something in a space where something was expected, no longer refer to anything at all. If you want to see more videos like this, click the video on screen now and make sure to subscribe.